So I wanted to clarify one thing from yesterday and then switch to discussing thermal physics. So we were talking towards the end of yesterday's lecture about these excited states. Where we had carrying, so our example was a coherent state of a created by some scalar operator. So two things I want to emphasize. So the first thing I want to say is that we argued for the state to be geometric. It's necessary for the energy to scale like n squared, and this came by looking at the fact that I was trying to explain yesterday, that the energy momentum tensor, the expectation value of energy in this state, which I denoted by k yesterday, scales like 1 over g Newton. I had meant to indicate that the energy density is a non-trivial function of the wave, and I didn't mean to indicate that the energy density is proportional to the wave. I think I miswrote that equation, which confused a few of you. So the energy density is proportional to 1 over g Newton. It depends on the wave. In fact, you can work out what it depends on the wave to be. For small o, the energy density should be quadratic. And that's because in the bulk, the scalar energy momentum tensor is quadratic in the field phi. Right? Because Einstein's equation tells us that r mu nu minus sorry, I'll try to stick to my conventions. I'll keep doing this all the time, but let me try to keep to my conventions that the bulk indices are Latin, uppercase. But Tm and phi right? And already here you see that since this proportionality constant is 1 over g Newton, unless there is 1 over g Newton inside the Tm and phi, you'll not get an order 1 contribution here. So g Newton, remember, is order 1 over n squared. Okay, so that's one thing I wanted to say. You can actually work out in some specific examples what is the actual form of Tmn of the wave. A bit more complicated. Okay, I'll give you an example. for it looks something like this generically. So let me talk about the TT component of the energy momentum tensor in this state K. And there are phases, depending on what operator you choose, where the energy momentum tensor starts out growing quadratically and has a sort of, it's a many to one map, so it's sort of not a function. It spirals in, or there are phases where it starts off quadratically and then monotonically grows. So these depend on details of the operator. And there's a sort of reasonable amount of literature on the subject, which I can direct your attention to if you're interested. Okay. So I hope that clarifies the discussion from yesterday, that this is not proportional to the wave, it's a function of the wave, which you have to determine by solving Einstein's equations with the boundary conditions I told you yesterday. So this plot I'm drawing came out of one such solution. Good? All right. So we talked about one class of excited states. There are many other excited states that people study, but I'm going to talk about one other aspect of physics that's quite interesting, and it touches upon interesting aspects of gravity as well, which involves studying thermal physics of field theories. So we can motivate this many ways. So let me motivate it by saying the following. So say you want to understand the spectrum of the field theory. So this you can do by just counting the states in a system with weighted by their energy eigenvalues. So usually you can encode this in a thermal partition function. Which is basically the sum over states weighted by their energy, where beta is the inverse temperature. So if we know this object, we can Laplace transform it and get from it the density of states as a function of energy. We can extract how many states there are at a given energy in the system. And you should all probably know that, for example, if you have a simple harmonic oscillator, then the spectrum is best encoded in this partition function z of beta, which is given by the sum Yeah? Just do the geometric sum, and you get the answer for the harmonic oscillator. So we want to do this for other states and understand what's happening in this context. Of course, what we have at hand is not a simple harmonic oscillator, which is easy to solve. It's not a free theory. We have something more complicated. We want to understand this kind of structure for interacting conformal field theories. So let me say one thing before we proceed, and then I'll tell you how to do it in the interacting case. For free theories, and in fact even free n equals 4 sup Yang-Mills, you can actually find the analog of this, find the partition function, explicitly. The answer is given as a matrix model integral and I'll refer you to the work of Roni Minwala and Ramzonk, Papadodimas, and one more person whose name I'm forgetting, from about a decade ago, who actually did this counting. Basically, it's a free theory, so again, you can decompose into modes, and you can sort of think of harmonic oscillators, degree of freedom, and add up the degrees of freedom. So they found one answer. They found something interesting there, which I'm going to talk about in a while. But all I want to say is that for the free theory, you can actually do this for now. But if you want to do the interacting case, you have to be a bit cleverer, because you actually have to know what the eigenspectrum of the Hamiltonian is. And we don't usually know the eigenspectrum of the Hamiltonian for interacting field theories. So this is where ADS-CFT comes to the rescue, because we can actually do this computation in the limit where we can describe our field theory by classical gravity. Yeah. It's given as an integral over a UN matrix It's a classical integral. It's not a path integral. Okay. But you have to integrate over a matrix worth of degrees of freedom. You can call it a path integral over matrices, but it's the same thing. Some function of, so let me call this f beta of m. So there's some simple answer you can work out. You can actually, in this case it's a free theory, so you can actually do the path integral. So what you want to do in this case is to start with the theory. So let me postpone how to do this, because it'll be a bit easier to tell you why the field theory is done that way in this context, and then you get this answer. But you can either do it as starting from the path integral, or more simply you could imagine doing this by just counting the states in the theory and summing them up along these lines. They both end up with the same point. They have to. It's the same counting. Okay. So I'm going to argue now that the thermal physics of CFT is described by the physics of black holes. In ADS spacetime. So I'll give you one argument now, and I'll give you an argument later that this has to be the case in the second lecture when we discuss entanglement. And the first argument is basically goes back to Mulder-Sanders decoupling. which we talked about in the first lecture, we can carry this out for non-extremal D3 branes, for which the geometry in 10 dimensions looks as follows. Where, as I said the other day, h of r, which comes from the number of D3 branes, is given as this function 1 plus r to the 4 or r to the 4, and this new function, which these days is called the emblackening function by some people, is just given by this Schwarzschild-like form. So what we can do is, given this solution, we can take the near horizon limit where the S5 freezes out, and what you're left with is a new geometry which is okay. So we end up with this new geometry. So if you ignore the S5, the 5-dimensional space with metric is a black hole in ADS which I will call the planar Schwarzschild ADS black hole. Okay, I'll explain why it's planar and why it's Schwarzschild in a second. But that's the solution you get, and it's sort of intuitively reasonable that the solution we get in this limit, we put some excitations, we've excited the system here, and then taken the decoupling limit, so we got some excited state. But what black holes tend to do is they allow you to excite all the degrees of freedom of your system to some finite temperature. And the claim we're going to make now is that the black hole thermodynamics that follows from arguments of Bekenstein and Hawking translates into thermodynamic properties of the field theory. Okay, so that solution, so the the 5-dimensional metric. So I'll call this the Schwarzschild ADS5 solution solves Einstein's equations with negative cosmological constant. So just excited geometry in this sense, and we can work out various properties of this solution which are useful for us. So I'm calling it planar because the horizon topology has translational invariance the spatial sections are a 3-dimensional flat space, right? Because I have 3-dimensional flat space coordinatized by x here, and they survive in the limit. So the geometry has killing fields d by dt and d by dxi for I equals 1 to 3. These are space-like. And this guy is time-like outside the horizon. And is the null generator of the event horizon. You've all seen black holes before, I assume. Yes? You've all seen the Schwarzschild solution in flat space. So this is similar, it's just that we are sort of working in a different space-time, so our asymptotics are not flat, our asymptotics are ADS, but the physics of black holes doesn't really care so much about that, so we can understand its properties just the same way as we understand the physics properties of black holes in flat space. So what do we want to know about this? So first, let's talk a bit about the causal structure to convince ourselves that there is a horizon and there is a black hole here. So to describe the causal structure, I'm going to draw a Penrose diagram. How many people have not seen a Penrose diagram before? Okay, some people haven't seen a Penrose diagram. Okay. So what we're going to do is we're going to we'll look at constant x slices and conformally compactify the space-time. To be able to draw the picture of bringing the horizon to finite distance, or bringing the infinity to finite distance. So it suffices for that purpose to just look at this part of the metric. And the first thing to realize is that the point of under conformal compactifications, if you do conformal rescalings, leaves causal structure intact, because if I take my metric and do a local while rescaling, the inner product between vectors changes, but since this is a positive definite function, time-like vectors stay time-like, space-like vectors stay space-like, and null vectors stay null. So we can choose a positive definite function and align things so that null rays in the space-time propagate at 45 degrees, like you tend to draw in space-time diagrams in special relativity. Okay, so that's the logic behind drawing those diagrams. You want to be able to tell by looking at a picture whether you can communicate from one region to the other, which you can do in special relativity if I just draw a space-time diagram in t and x, because you can communicate in the part of the space-time diagram which is below the 45 degree line, and which is above the 45 degree line if time runs up. If this is flat space, then the light cones open out, and we want to maintain that structure even in this space-time. So this is a time-like domain. This is space-like. And we want to retain this structure as we work in arbitrary curved spacetimes. So that's the logic behind Penrose diagrams. Okay. You can be a bit more ambitious. What you can try to do here is to write down tortoise coordinates, pull out various factors, and do the explicit coordinate transformation that brings it to some form that you recognize. I'm not going to do that. I'm just going to give you the logic and then draw the answer for you. Okay? But essentially, you could sort of convince yourself that all you need to do is write the metric as in terms of some coordinates d rho squared minus some function of rho dt squared after having pulled out various factors. And the art form here is basically working out what is the right coordinate system to use so that things come to finite distance. See, rho runs from 0 to infinity. R runs from 0 to infinity, so you want to bring rho from r equals infinity to rho equals finite value. So some function like rho equals tan r, r equals tan rho will do the job, roughly speaking, because when rho hits pi over 2, r will get to infinity. So by playing around with functions of this kind, you can bring the metric to a form that you can sort of recognize quite simply. So if you do this exercise, you find the following. This is the Penrose diagram for area Schwarzschild. This is the r equals infinity domain. This is parameterized by t. I'm taking a slice at constant x. So x runs out of the there are three x directions which I'm suppressing. They run out of the board. This is the boundary where the CFT lives. Which is copy of Minkowski space. As you lines of constant t runs, orbits of t run this way, d by dt orbits. And because this function f of r, which was because this function has a simple pole, simple 0 at r equals r0, it follows that this killing field d by dt, which is time-like for r bigger than r0, goes null at r equals r0, which is the location of the event horizon. If you go through, you will find that the signature, the lines of constant t become time-like, and so inside you have a black hole and a singularity at r equals 0. So the TR coordinates cover only this wedge of this triangle of the space-time. If you want to describe the entire space-time, we have to pass on to some analog of the Kruskal coordinates for the entire space-time here. But you can find the Kruskal coordinates basically by doing the same tricks that you would do in flat space. So define a tortoise coordinate by writing dr star so that and then you can write the metric in standard Kruskal form by pulling out factors of fr squared, and then if I write it this, okay, let me do two more steps and it will become clear. So dr squared is I just have to redefine t plus minus r star as u and v, and then absorb this factor into this to write down a simple metric which is regular everywhere. By absorbing this factor of f of r into them. Okay. So these are the steps you would usually do to go from, so this is some Kruskal coordinatization. Which you can obtain by just following a standard textbook, whatever you see in the, for the Schwarzschild black hole in flat space, by just playing the same game with a more complicated function. For Schwarzschild black hole, the function is just basically replace f Schwarzschild, which is 1 minus 2m over r, by f of r here. That's all. The key difference is this factor of r squared, which and the powers here, which come from the fact that this is an ADS black hole, it's not a flat space black hole. And just as in the maximally extended Kruskal diagram for Minkowski for Schwarzschild black hole, you see that as you go through the horizon, you encounter a second asymptotic region, which also has r equals infinity, and I'll interpret this with another copy of r3, 1, and I'll interpret this in some time. For now, we are not going to worry about it. Let's just talk about this right causal diamond, which is the domain of outer communication of the black hole. Okay. Any questions about this? For those, especially those who have not seen this before. Okay. Okay, so this is t equals 0 slice, and then time marches up with t being plus infinity at this point. Time marches down here, and t equals minus infinity is down here. Okay. All right. Yeah. Yep. Good. So the Schwarzschild black hole Penrose diagram looks like this, and you're right that it has a Scri minus, which is null infinity, and a Scri plus, which is future null infinity, and the horizon structure is the same. The difference here is that we are in asymptotically ADI space-time. So the null infinity, which is the place where null geodesics start from and go back to, is not null. It's time-lag. Right? We already saw that ADS has a time-lag boundary. All the null geodesics in ADS started there, and they went back there. I told you that null geodesics, one of your exercises was to work out null geodesics in ADS, and see that they start at the boundary and go back to the boundary in finite coordinate time. So ADS doesn't have this time like these null infinities of Minkowski space. It has time like null infinity. So that's why I've drawn it as a vertical straight line. In fact, because of that fact, you can actually realize one interesting thing. So this diagram for Schwarzschild is accurate. So you could try to ask, suppose you actually want to plot the Penrose diagram, which you can do. I mean, people usually just draw it, but you can actually plot it by picking some usual coordinates and putting some coordinate grid and seeing how to do it. In flat space, these guys are at 45-degree lines because they're null lines themselves. The infinities are null line themselves, just as the horizons. Now, let's say I want to make them time-like, so I want to squash them to make them 90-degree vertical lines. If you do that, you will see that a conformal transformation that folds them in necessarily folds down the singularity. So you cannot keep the infinity straight and the singularities horizontal simultaneously. And one consequence which wasn't appreciated till past area safety was invented is that a Penrose diagram for ADS black holes, it's best drawn with singularities bent down if you actually want to bend in down towards the bifurcation surface if you want to understand the causal structure properly. Yeah. But this is worked out in a very nice paper from about 10 years ago by Fitkowski, Hubenish, Schenker, and Kleban. But it's something that you can just do back of the envelope yourself to check that it is true. You can write a simple code to actually plot this. If you follow my steps, you can do it in like a short order. You can just try to plot the Penrose diagram in Mathematica and see that the structure is exactly what I'm saying. Okay. So what do we know about this black hole? So we know we have its causal structure. We see that there's a part of the space-time which can't communicate to this boundary. And we've grown this other asymptotic region, which for now is just going to be left aside. I'm going to come back to it later in the afternoon. What we know is that the horizon at r equals r0 has an area which is because the metric, remember, to compute the horizon area, you need to look at the horizon at a constant time and ask what the spatial area is at that instant of time. So induced metric on spatial slices is so I'm just slicing it at some instant of time here and asking what the area of that surface is. And we know that Bekenstein and Hawking taught us that associated with this area is an entropy, the entropy of the black hole, which is this area over 4 times g Newton, which is okay. Secondly, we know that the black hole has temperature. Which you can determine either by computing the surface gravity or doing the trick of working in Euclidean space. Which I will do. And show you for in a second the temperature is R0 over pi. Okay, so if you compute the surface gravity, you should find that the surface gravity is defined as kappa squared is minus half grad m psi n, grad m psi n, for the killing field psi being d by dt, and you should find this answer by realizing that temperature is kappa over 2 pi. But let's not try to compute covariant derivatives of this vector. Let's try to do a much simpler calculation. Let's look at the Euclidean black hole, which I will obtain by analytically continuing T to IT. Okay, I can do this because T is a killing field. Change the static outside the horizon section of the black hole. If you like, what I'm going to convince you is that there's a complex. If you think of this time as a complex direction, the real time section is what I've drawn here, and there's a complex time circle that's going to run around, going between the two boundaries through the horizon. But for now, let's just do this trick and look at this two-dimensional slice, which looks like what was it? R squared f of r dte squared plus dr squared. I'll ignore the spatial part. It's not essential for what I'm going to do. So as you go to infinity, this goes to r squared de squared plus dr squared over r squared. Because it's a function f of r goes to 1, that's what you expect is asymptotically ADS. But as r goes to r0, it goes to r0 squared, r minus r0, and you can convince yourself that actually goes to plus corrections which are order r minus r0 squared, plus which terms I'm dropping every term which is higher ordered. I'm just keeping the leading Taylor expansion metric coefficients in the r minus r0 expansion. So change coordinates to call this the epsilon squared, and you'll find that this becomes r0 to the 4 f prime r0 squared epsilon squared dte squared over 4. So what is this telling us? What this is saying is that this section, the RT section of the black hole, has the topology of a disk with TE parameterizing a circle, R running out, and this circle terminates. So if you sort of look at this disk, this side from side on, it's really a disk with r equals r0 being the origin, and the times are TE running around this circle, and sections of constant TE have proper size determined by this function f of r, but in particular they shrink to 0 size. The TE circle shrinks to 0 size at r equals r0. But since it shrinks to 0 size at a rate given by, in these local coordinates, by epsilon squared, in the neighborhood of this, which is where my coordinates are valid, these epsilon coordinates are valid, it follows that if the geometry is smooth, locally this should look like the origin of two-dimensional flat space in polar coordinates. Right? So if I look at a disk, if I look at a point in a disk in flat space and write if I write the metric in flat space around in polar coordinates, then I would have the epsilon squared plus epsilon squared times dTe squared. I'll put tilde here, with TE equals TE plus 2 pi. T tilde E equals T tilde E plus 2 pi. Right? Polar coordinates are regular only if the angle traverses 2 pi. Because if the angle doesn't traverse 2 pi, you don't have a disk, you have a pizza wedge with if the angle doesn't traverse 2 pi. You have a singularity here, you have a conical singularity when you've cut out a disk, cut out a wedge from the disk. Okay? So for the geometry to be smooth, you want this coordinate in these, when you've gone to local coordinates around the origin, you want the angle to cover a full 2 pi circle, so that you have a circle, not a wedge. Which means that here, from that, regularity requires that TE, which is, the map from T tilde to T is just a rescaling. T tilde is r0 squared f prime r naught. Oh, there's a factor of 4 here, by 2. So I need this Euclidean time coordinate to be a circle with period 4 pi over r naught squared f prime r naught. And a Euclidean circle sets the boundary conditions for thermal boundary conditions. Why is this? Do people know why this is? This is a statement in quantum mechanics. See, quantum evolution is done by the unitary e to the minus iht. If you want to evolve in imaginary time, by amount beta, then this evolution operator becomes e to the minus beta h, which is what I motivated studying thermal partition functions by. So the thermal density matrix, which is this operator e to the minus beta h, is the operator that does imaginary time evolution by I beta. So if I tell you that time is, if I have Euclidean time which is compact, it just means that I'm doing finite temperature physics with a period set by the size of the compact time circle. So thermal physics is the same as Euclidean quantum field theory with time circle setting, period of time circle setting. Beta, and if you just translate all these parameters that I've been using, then you can differentiate f prime, etc., and you'll find that temperature is the answer I quoted, R0 over pi. Yeah. So temperature is R0 over pi. Black hole entropy is area over 4g Newton, area horizon over 4g Newton, which was R0 cubed, volume R3 over 4g Newton, which is the same as T cubed pi cubed volume R3 over 4g Newton, which if I translate to field theory units gives me pi squared over 2 n squared T cubed volume. Okay, it's helpful to know that if you do the translation correctly, 1 over 16 pi g Newton is n squared over 8 pi squared. Rather, ADS radius cubed over 16 pi squared. Okay. I'm using some facts of how to normalize things, but okay. Does this ring a bell? Does this tell you anything? How many people know Stefan Boltzmann's law? Sir? No. Or how many people don't know Stefan Boltzmann's law? Everybody knows Stefan Boltzmann's law. So Stefan Boltzmann's law says that the pressure in a photon gas scales like T to the 4. So entropy is one derivative of pressure. Entropy scales like T cubed. Do you know why that is? No? Okay. So entropy is dimensionless. Energy has dimensions, entropy is dimensionless. A conformal field theory has no scales. So what can entropy scale like at finite temperature in a conformal field theory? Sorry? Yeah, what is the so forget about the central charge dependence. What is the temperature dependence? Cubed, yes. Why is it cubed? Huh? Oh, no. We are in higher dimensions. We can't use the short-chain derivative. Yes, but yeah, in 2 dimensions your argument would be fine, but in higher dimensions you have to be a bit more careful. See, entropy is extensive, so it has to scale with volume. There's only one other function, there's only one other scale in the problem, which is temperature. So all the power of spatial volume has to be compensated by powers of temperature. So it's 3-dimensional volume, so it has to be compensated by 3-dimensional T cubed. So even if you didn't know anything, this is the answer for a conformal field theory, which is the answer for okay. The non-trivial coefficient, non-trivial piece here is this piece. So that is, if you didn't know ADS-CFT, you would have come to this point and realized, but black holes in ADS space-time behave like a gas of conformal particles at temperature T. What you wouldn't know is how many particles you have. That's buried in this coefficient. So the prefactor, which is n squared pi squared over 2, is a gravity prediction for the density of states, for the number of, for the states in the CFT. At strong coupling. And this answer was first derived by various people, Klebanov and Gubser and Pete, I believe, much before Maldasena's paper. So they realized already that D branes, without even taking the decoupling limit, they realized that D3 branes have features of conformal field theory in 3+1 dimensions. What they were confused about is the following fact, that if you look at free n equals 4 super Yang-Mills, the entropy behaves like, okay, so let me convert this entropy into a free energy. So this, and the free energy is 4/3 the free energy you get from gravity. Okay, to convert entropy to free energy, you just use the first law, dF equals S dt, and integrate. S is dF dt. Because the free energy is E minus Ts. To minus sign. Free energy is negative. Yeah. Okay. So there was a confusion initially, which is how is it that there are two functions where, so I already told you that this piece of the function has no information. T cubed volume is information free. So why do you, so you of course expect this to give you that, but why is there a factor of 4/3? So it was only after Maldaceno's paper that people realized that, but this is sort of obvious, because if you look at this theory, as a function of coupling, you're computing some answer here for the free energy. As a function of lambda, you get some number which will normalize to 1, but then you get some answer here which is 3/4 that number, and that makes perfect sense, because if you make the theory more interacting, you expect that somehow the number of degrees of freedom you're left to play with gets decreased. The free theory is maximally free. All the particles you throw in can contribute to the total entropy of the system. But once you have interactions, it just might so happen that some of the particles combine into some and stay bound to each other, and you don't have access to as many degrees of freedom as you have in the free theory. So area CFT gives you a prediction that somehow you should see a decrease in the number of active degrees of freedom at finite temperature as you go from weak to strong coupling. And today, what we know is that if you compute the correction in perturbation theory in lambda, you see that the entropy, the free energy, does decrease. And if you compute using corrections to supergravity, what this function does, you find that this function increases. So then you can guess that somehow there is some kind of monotone decrease as a function of coupling that goes from one corner to the other. But nobody's ever been able to compute this quantity at any intermediate coupling. So we know something in the neighborhood of the origin, and we know something in the neighborhood of infinity. Okay? Any questions about this? No? All right. You can translate this into many other statements, and I'll make one statement. The equation of state, which follows from this formula for the entropy as a function of temperature, is E equals 3 times pressure times volume, which gives the speed of sound which is 1 over root 3, which I'll come back to later. Okay. Again, this is not a miracle. This is another artifact of conformal invariance. This follows from the fact that the expectation value of the energy momentum tensor has to have 0 trace in conformally invariant states, and that immediately tells you that the energy component has to be balanced by the pressure components. So if you know this, you can work this out, but if you know this, you can work that out. They're the same statement. Thermodynamics. The argument that led to this diagram. So in free theory, I told you there was a counting done. You can do the free energy calculation. Then you can try to do the free energy calculation at small lambda. So you do one loop corrections with lambda perturbation theory, and what you see the fact is, you know that you will get, once the dust settles, you know that you'll get n squared t cubed out. That's sort of guaranteed to you. N squared is the number of SUN degrees of freedom that are there in the system. T cubed is guaranteed by conformal symmetry. You have to work out what the coefficient is. So there's some coefficient which is now a function of lambda. And what you see in perturbation theory is that coefficient sort of is negative. It decreases you from 0. but this is the leading order perturbation theory calculation, so it's just telling you that the gradient away from the free theory is in the direction of decreasing the free energy. Okay. Here, it's a bit more involved. You need to know how to do finite lambda corrections away from Einstein's supergravity. So they have to come from string theory. And the string theory corrections, the finite lambda corrections in string theory, are L string corrections. Because L string over L ADS was related to lambda. 1 over n corrections were L Planck corrections. Okay. So since these are L string corrections, you can take the answers from string theory and repackage them into modified gravity dynamics. I'll just call it modifications to Einstein gravity. Okay? So what you really find is you find that instead of solving for a black hole in Einstein-Hilbert theory, you have to solve for the black hole in some Riemann to the fourth theory, which is a particular theory with 4 derivative couplings, which naturally comes out of string theory. Okay, so this effective action is known. People have computed this effective action for some subsector of string theory, and you can try to solve classical equations of that, find the black hole solution, find its entropy, find everything, and see how the entropy changes. Okay, so this was done by Gapser and various people in the late 90s. But it's basically solving a more complicated gravity problem. So if I remember correctly, the answer involves, it's a 1 over lambda correction, and it's 3/4 plus 1 over lambda times some zeta of 3 or something like that. But to get that information, you need to know what this theory is. And like any perturbation theory, it's impossible to start here and get the answer somewhere here in the middle. That's finite distance away from in perturbation theory. So you can do a lambda perturbation theory here and a 1 over root lambda perturbation theory here. This is the right parameter, but intermediate things are sort of off limits to both of these perturbation theories. It's an interesting question whether one can do better. So some of you might know about statements that have been made in the integrability community, where there's a sector of n equals 4 super Young that's integrable. So people have tried computing some anomalous dimensions of various operators using those techniques exactly as a function of lambda. Okay. The problem is that those techniques don't directly extend to this domain, because we are asking for energies and free energies which are of order n squared. Integrability is only valid for states which have at most energies of order n. Okay, so we need some new ideas if we actually want to be able to compute this function explicitly. I'll make one more comment about this in a second when I draw one more picture and show you one other thing. But any questions? Any other questions about this? No? All right. So let me switch gears for a second, continue with black holes, but let me tell you one other fun fact about ADS black holes. So we studied thermal physics in flat space, right? So and that was actually simple because there was no scale in flat space, so the entropy was completely determined by scaling relations. So what happens if we study thermal physics in compact space? Say I want to study thermal physics in S3 cross R. Now I have two scales. There's the radius of the S3 and the temperature. So clearly for R times R S3 times temperature is a dimensionless parameter. So even though I have a conformally invariant theory, once I have a dimensionless parameter, I can start having non-trivial dependence on the dimensionless parameter. So scale invariance doesn't determine the dependence on this parameter anymore. What we know is that for this much bigger than 1, we should go back to the previously studied case, right? Because taking this limit very this parameter very large can be achieved by taking the size of the sphere to be very large and just decompactify the sphere. But it can equivalently be done by staying with a finite size sphere and taking the temperature to be very large. So the high temperature physics on S3 cross R has to agree with the predictions that I just told you. But we don't know anything yet about the low temperature physics. So why it goes to flat space physics? See, when temperature is very big, what it means is that thermal wavelengths are very short. So you have a compact space, but thermal particles don't see the compactness of the space. So why did people in the Middle Ages think Earth was flat? Same reason. So, but we don't know anything about this. This logic doesn't tell us. So let's even say order 1. And there's room for something non-trivial to happen. And you might wonder whether there is a phase transition. Now, somebody should object, saying that I'm in compact space, so I can't have phase transitions. I hope everybody knows that in compact space you don't have phase transitions, right? But we've done something funny, because see, phase transitions can only happen in thermodynamic limit. So you might have thought that there's no scope for phase transitions because the thermodynamic limit is this limit, right? So let me pose the question: can we have phase transitions? And give you the straw man. The straw man simply says in compact volume, so no phase transitions. The usual argument just says the partition function in compact volume is like that of a discrete quantum system. So you have an analytic partition function. So how can an analytic partition function have singularities? No, the only way you can have singularities in a partition function is if you can take the thermodynamic volume when the partition function can develop singularities. So, but I told you this is a straw man. So there's a way out. What's the way out? The way out is that even though we are still in compact volume, we are doing a large N theory, so we have infinitely many degrees of freedom. But so this would be a large N phase transition in the sense that, strictly speaking, at infinite N, you would see non-analytic behavior, but at finite N, you would see that sort of smoothed out by some crossover. If there is such a phase transition, and what I'm going to convince you is that there will be a phase transition in this theory. Okay? Is that argument clear? This is a reasonably important piece of argument, but what I'm going to show you is that gravity indeed predicts this, but this is what you should have expected from field theory. Okay. All right. So let's go to gravity and ask, what can we learn about this from gravity? Well, so let's do the problem as follows. So thermal physics on S3 cross R can be studied by this big rotation trick So let me take my boundary to be, so we'll pass to Euclidean ADS-50. And we'll take as boundary to be S3 times S1 thermal circle with period beta. Okay, I just showed you how to do that. In the flat space case, I can just do the same thing because time just goes along for the ride in this case. So what are the rules of ADS-CFT that I told you yesterday? The rules of ADS-CFT are, if I give you the boundary, you try to solve Einstein's equations with those boundary conditions. So we need a 5-dimensional geometry with the boundary of M5 being B4. M5 solves Einstein's equations. With this in ADS. Now, so far we've been looking at examples where the solution to our boundary conditions was essentially unique. I'm not going to argue to you that the solution in this case is not unique. There can be more than one solution with these boundary conditions. So what do I have here? I have M5, my boundary is a 4-manifold, which is a 3-sphere times a circle, and I have a radial direction, which is going away from the boundary into the interior. Now, one of two things can happen. We already saw in the previous case that the circle could shrink to 0 like in a disk as I go towards the interior of the space-time. That was the black hole geometry. But why can't it be that this sphere shrinks to 0 and the circle stays finite? So even without solving Einstein's equations, just at the level of topology, the two distinct topologies for M5 it can either be topologically what we saw before. It could be a 3-sphere times a 2-ball, or a disk, where the circle is shrinking to 0, or it could be a 4-ball times the circle. They're distinct. In this case, they have different homotopy classes. In this case, there's a non-contractible S3. In this case, there's a non-contractible S1. But of course, you know, this is topology. We have to answer dynamics. The question is answered by solving Einstein's equations. So here are two solutions. Here's the first solution. So I'll call this 1. And I'll call this 2. They're not hard to find because in either case you're maintaining spherical symmetry, you have time translational symmetry, so you just have to solve some ODEs. And so they are, I mean, you didn't even have to solve them because people had solved them a long time ago. And these functions are simple. Here, you will recognize this function. The second solution, where the geometry is topologically a 4-ball times a circle, I just take the usual ADS solution, the global ADS solution, and analytically continue time. So f is 1 plus r squared. At r equals 0, the 3-sphere shrinks to 0 size, like at the origin on R4. But the time direction, the Euclidean time direction stays finite size. It has size 1. Yeah? This solution, on the other hand, let me write it in a useful parameterization. Looks like the black hole solution that I had. But I've parameterized this mass function by this parameter r plus for convenience. You'll see why in a second. So how would you find these solutions? The geometry looks very much like flat space, except that it's asymptotically ADS. So 1 plus r squared tells you it's ADS, global ADS. If I want to find a black hole in ADS, a Schwarzschild black hole in ADS, I write down the 1 plus r squared and then write down the usual Newtonian potential for a point particle in d dimensions. If we're in ADS 5, in 5 dimensions, the Schwarzschild black hole would have had a 1 over r squared. The Newtonian potential will fall off as 1 over r squared. It won't fall off as 1 over r as it does in 4 dimensions. So that's the answer. So this is the global Schwarzschild ADS black hole, the first solution. And this is just a space-time where it's ADS, except that I have compactified the thermal circle, and I'll call it a thermal ADS space-time, the second space-time. Okay? So we have these two facts. Now we can ask ourselves, okay, we have two solutions, but what are the rules of the game? How do we know which of them is important to us? So given the boundary conditions, these two solutions exist. And where do what is their where do they dominate, etc., etc. So to answer that question, I need to do the calculation here. So clearly, okay. So for the thermal ADS case, we can have any temperature all I need to do is take TE to be periodic with period set by the inverse temperature. This circle is not doing anything funny, it's just staying, it's changing its size as I go from infinity to some finite value at the origin. You can set the size to be whatever you want. Solution exists for all temperatures. Okay? So it's a one parameter family of solutions parameterized by the size of the circle. And I'll measure the size of the circle at infinity because that's the size that tells me what the temperature is. So we have a one parameter family of solutions. For global Schwarzschild ADS, the temperature, if you follow my previous logic of going to the Euclidean space, working out the period of the circle at the origin, you find the translation tells you that beta is this gadget. Okay, let me put this LADS here just to keep dimensions right, but I'm aware that I'm sort of switching in and out of putting the LADS. So in the solution I've switched LADS to 1, but I put it back here. You can put it, determine what it is in the solution by scale, by dimensional analysis. So horizon is so I chose this function 1 plus r squared minus r plus squared 1 plus r plus squared over r plus squared, so that the horizon is at r equals r plus. Okay, that's why I parameterized it this way instead of writing some parameter m here, because then I have to solve a fourth order equation to find what m is, where the horizon is. Okay, that's nice, but you see one fact. Let's plot this. Let's plot the temperature we get from here as a function of r plus. For large R plus, the temperature goes like R plus. Temperature is 1 over beta, it goes like R plus. For small R plus, the temperature goes like 1 over R plus. And this curve has a turning point. It has a minimum temperature, allowed temperature, which you can work out. I think it's some it's basically at some R plus equals 1 over root 2 L ADS or something like that. Okay, if I remember correctly. Right? So, surprise, surprise, we don't have a solution for all values of temperature. And when we do have a solution, two solutions for the same value of temperature. So for T less than T star, turning point, we have a unique solution which is thermal ADS. But for T bigger than T star, we have three solutions. Because parameterized in terms of temperature, this is double valued. So I have two solutions for a given temperature. I'll call this branch the small black hole branch, and this branch the large black hole branch. And we can understand the distinction between the small and large black holes as follows. These small black holes, so this is R plus of order LADS. I think it's just 1 over root 2 is correct. So the small black holes are of a size that's smaller than the ADS size. So they are like flat Earth society people. They don't see the ADS curvature. They're sitting in ADS, but they don't see the fact that there's a curvature radius of ADS. So as far as they are concerned, the smaller they get, the better they're approximated by Schwarzschild black holes in flat space. And you know one fact about Schwarzschild black holes in flat space, which is that temperature increases as their size goes down. It's the famous fact that flat space black holes have negative specific heat. This is what happens here. The fact that this slope is negative tells you that these black holes have negative specific heat. So the smaller you make the black hole, the better it's approximated by a flat space black hole. It's funny thermodynamically. So clearly this cannot be dual to a sensible quantum field theory thermodynamics, because there is no reason why our quantum field theory has negative specific heat. Negative specific heat indicates thermal instability, which is not the case for these guys, for our conformal field theory. Large black holes, on the other hand, have positive specific heat. So they should be viable solutions in principle. So first of all, we can forget about this half of the solution branch. So if anything will ever make any sense thermodynamically from the field theory point of view, it's these large black holes. And we already know that when the temperature is very high, when we are high up along this curve, which means when the black holes are very large, we are in the limit of the planar solutions, or we are in the limit when we are doing field theory on flat space. So the black hole should dominate, right? Because this global Schwarzschild area solution should approximate very well the planar black hole solution we used for studying thermal physics on Minkowski space. So large global Schwarzschild areas black holes should be well approximated by planar Schwarzschild areas black holes. And again, it's the same point, that the large black holes have a very big sphere on their horizon, and that very big sphere can be, for all intents and purposes, if you're not looking at the thermal scales, be approximated by a plane. But now it's clear there has to be a phase transition. Because at high temperatures, we are in the black hole phase. At low temperatures, we don't have a choice. We can't be in the black hole phase. There is no solution at low enough temperatures. Now we have to find out where the transition happens. Okay? To determine the transition point, we should compare free energies. And to do that, let's remember that the part we said the CFT partition function is, or we wrote the formula the other day for CFT correlation, generating function of correlation functions. I'm going to translate that into a free energy statement now, which is correlation function, the identity operator at finite temperature. So this is trace in the CFT of e to the minus beta h, and this is given in the saddle point approximation by e to the minus I bulk with boundary conditions this is the I bulk is the on shell action for gravity. So you find solution to Einstein's equations, plug them into the Einstein-Hilbert-Lagrangian, and compute the answer. So I is given by I on shell. If I use Einstein's equations and replace the Ricci scalar by its let me put the 8 pi g Newton here, d5x 4 root g. I put E here to indicate it's Euclidean. And you have to compute the volume of the spaces in the two geometries. Because the Ricci's case, we're solving Einstein's equations with negative cosmological constant. So R mu nu is lambda g mu nu. So R is a number proportional to the cosmological constant. I've used that fact here in writing this answer. So we have to take the metric, compute the determinant, plug it in, and compare them correctly. And what you find is I black hole minus I ADS looks like, okay, various factors, pi squared R plus cubed over 4g Newton, L ADS squared. You have to exercise a bit of care in doing this computation. What I have done is I have you have to compare them with the same temperature. So there are two geometries, two different spacetimes. They're computing on-shell action for both of them. You have to, and the volumes of these spacetimes, because the ADS, they will diverge. So you put a regulator and you compute the finite difference between the two objects, but you have to compare them with the same regulator so that the circle of time at infinity has the same size in both regulation schemes. Okay, so that can be done. You get this answer, and you see that, well, the solution which has smaller free energy wins. So the solution that wins is the black hole when the size is bigger than the ADS size. And below the ADS size, the thermal ADS dominates. So even though the solutions begin existence here, the black holes don't start dominating till a bit later. And after that, you're in the black hole phase. So the phase diagram is such that, so below this temperature, you're dominated by thermal ADS. And above this temperature, you're dominated by black hole phase. So I should point out that this calculation was done eons before ADS-CFT. Hawking and Page did this calculation. They were just interested in dynamics of black holes in ADS. So they realized that there is this phase transition in 1984, when most people in the world didn't care about ADS spacetimes. But it was revisited by Witten right after ADS-CFT, to emphasize that physics of conformal field theories in compact volume has interesting structure at large n. All right, so we started a bit late, but I will end on time. So let me tell you one thing and then stop. So you can repeat this exercise for other dimensions. It's all the same thing. There's one useful fact to remember. That I told you that you can do the counting of operators in n equals 4 super Yang-Mills in a free theory. It also reveals a phase transition. At finite temperature, again large n, and that temperature doesn't quite agree with this value, but again, it's a strong weak coupling issue. So there's non-trivial phase structure even in the free theory. If you count the number of operators below a certain scale, there are far fewer operators than at higher scale, and you can extract that from here as follows. Since for t less than t critical, thermal ADS dominates, the free energy is what I would call order 1. In other words, the thermal ADS solution is just the ADS spacetime. So when we compute the energy momentum tensor, you'll get 0. Right? It's the same vacuum spacetime that we encountered before. So the vacuum has 0 expectation value for the energy momentum tensor. I took that spacetime and analytically continued it. I should still just have the 0 for the energy momentum tensor. What it means is that this statement should not be interpreted as saying that the energy momentum tensor is exactly 0, because it's a gas of thermal particles in ADS, so they will have fluctuations, statistical fluctuations. So they will contribute some non-zero free energy, but those will come from doing quantum loops in the bulk. And we saw that the only way we can get quantum loop corrections is by doing 1/n corrections. So the right statement to make is that the leading order answer comes from quantum effects in thermal ADS, and that's why it's order 1. It's subleading in the 1/n expansion. Okay? Non-zero free energy comes from bulk quantum effects, which are 1/n squared suppressed. In the black hole phase, the free energy is order n squared, because it's a black hole that it has energy of order n squared. The entropy was order n squared. So when you compute the free energy, it's order n squared. So what you see is that for low temperatures, or equivalently, if you translate by Laplace transform, to a density of states, there are very few states in the system. The majority of the states that contribute to entropy, they can be activated only by going to high enough energy. So what this means is that this has been taken. So this is a useful fact to know, because we started ourselves asking, someone asked me, can I construct a holographic theory for something? And here's a partial answer to that question. Yes, you can, provided your theory has a very funny spectrum. It has very few states at low energies and very large number of states above some energy gap. So holographic field theories are all like this. if you look at their energy spectrum, below some energy, there's a very sparse spectrum, there are very few states, which implies that the free energy is order 1. Low energies translate to low temperatures by the Laplace transform, but above some critical energy, the large number of states, they're very, very large, the spectrum is very dense. So, if you have your favorite quantum field theory and you can diagonalize its Hamiltonian finite spectrum, if it happens to fit this characterization, then you're in good shape to try to come up with a holographic dual in terms of classical physics. Even this does not guarantee that it actually gives you classical gravity, but at least it's classical. If it doesn't do this, you have to try to solve a quantum string problem. Okay, I'll stop there. Oh, sorry, are there questions? Lunch break. Okay.